Hello everyone. This section we are going to learn integral test 11.3. Let's take a look. So before we do the integral test, I'm going to show you a theorem. Let's see. The theorem says if the series converges, then the partial sum have to be bounded from above. Let's take a look. Theorem 1. A series an of non-negative terms converges if and only if its partial sum we did the definition in the last section, Sn, they are bounded from above. We don't do the proof, but I can give you some basic idea of this thing. So partial sum, you can see, because all the terms are non-negative, so Sn plus 1 is larger than Sn, right? It's getting larger and larger. And if Sn are not bounded, so you can see when we keep going, so less will goes to infinity when n goes to infinity. In that case, this series will be diverges. So in order to be converges, it has to be bounded. Sn partial sum has to be bounded. Now let's take a look at the definition. This definition is called harmonic series. This is also a very often commonly used series, similar to geometric series. But let's see, this series converges or diverges. Harmonic series is given by this way, 1 over n. And if we write this out, look like this, 1 plus 1/2, 1/3, and then plus 1 over n plus, okay, this series. Now let's take a look. This converges or diverges. We are going to do this way. We are going to find the partial sum. One-third, 1/4. We're going to combine those terms together. Over 9 over 10. Okay, let's write down the first 16 terms now, and let's see. And the first term for the third, like a third bracket here, 1/3 is greater than 1/4. Is that right? And the 1/4 plus 1/4, so the whole term equals, the whole term here is greater than 2/4, which is 1/2. And the same thing here, we make for this 1/5 is greater than 1/8. This is greater than 1/8, greater than, and greater than 1/8. So the sum of those four terms greater equal to 4 over 8, which is also 1/2. And the next one, this is greater than 1 over 16. Same thing, actually this term is greater than 8 over 16, which is also 1/2. So by doing this way, we can write down our partial sum as 1 plus 1/2 plus, actually greater than 1/2 plus 1/2 plus dot dot. Okay, and we can also write down this into another way. If we have k term here, k 1/2, so it's k over 2. And when n goes to infinity, that means we have infinity terms. So definitely k should also goes to infinity. In this case, you can see Sn is unbounded, right? Sn actually goes to infinity, unbounded. So we can get to the conclusion. This one diverges. Harmonic series diverges. You don't need to know the proof here. Here I just show you the reason. In the future, we are not going to use this way to say. We can just remember harmonic series always diverges. Okay. You just need to know what is harmonic series and harmonic series diverges. We can also say example 1 here. Harmonic series. Okay, keep in mind harmonic series diverges. Next, let's take a look at the theorem 2, which is integral test. It's called integral test. Let's take a look at the test. Right now, we have a sequence an be a sequence. So when I write down this way like a bracket, this means sequence, right? List of numbers of positive terms suppose an equals fn. Do you remember what's the meaning of this one? It's kind of if an equals n over 1 plus n, something like that, and the fn is same thing, this equals fn. So we usually like to write down fx, right? We know what is fx, x over 1 plus x. When we do the L'Hopital's rule, we change our sequence into function, right? Something like that. Because for the integral, we cannot do the integral for the sequence series. We have to do the integral for function. That's why we like to set up a function where f is continuous function, f is continuous positive decreasing function of x for all x greater equal to capital N. Then the series n start from n to infinity an and integral, and this is improper integral, fx dx both converge or both diverge. Here we are not going to do the proof of the whole series, but I want to let you know why we can set up series, and we can say series and integral, they have same convergence divergence property. Why we can do that? Okay, just a basic idea. Let's take a look. We learned the integral definition in calculus 1, right? Calculus 1. So what's the meaning of the definition? This means the area under the function from a to b. For example, if we look at the function y equals x squared, y equals x squared, from A to B. Here, let's choose A and B to be, for example, 0 to 5. How about we can make it 0 to 5? So when we just introduce the definition for integral, we say we want to estimate the area under the function. So we divide 0 to 5, this interval into 5 pieces. For example, if we make them n equals 5, divide into 5 pieces, 1, 2, 3, 4, 5. And then we can estimate the area by those rectangles, the sum of those rectangles, right? If we look at the sum of those rectangles, the first one is just here is 1 is the height, and the base like A1. We have 5 rectangles, A3, A4, A5, and those are 1 plus the second height. I'm just going to label the second one. You will see the height is 1 over 2 squared. It's now 1. Sorry. This is 2 squared. Because as there is 2, x is 2, so y should be y squared. So that's going to be 2 squared. And for the rectangle, second rectangle, the base is 1, right? Something like that. And then 3 squared times 1, 4 squared times 1, 5 squared times 1. So you can see, actually, we can, if we write down this as a series, it's kind of 1 plus 2 squared plus 3 squared plus 4 squared plus 5 squared, something like that. So, and we use this to estimate the integral, and we can write down this as integral like this one, 0 to 5, something like that. And right now we can look this as series, and we can look this as the integral. So sometimes, they have almost the same sum. And in our case, we just change this into infinity. And here we have infinity terms. Okay, that's what's the meaning of integral test. And there are several things we need to pay attention. The first thing in the series, now let's take the theorem. Let's take a look at the integral test. First thing, the sequence an, they have to be positive. Okay, the first thing, they have to be positive. We cannot have sometimes positive 1, negative 1. We cannot have alternating thing, something like that. No, it has to be always positive. Okay, the first case. And then the function is continuous. The function is continuous, positive, decreasing. Okay, and then we have, be careful here. If the series start from capital N, our integral start from N. Okay, this improper integral. They have the same converges, diverges. So in next example, I'm going to show you how to use the integral test to show a given series converges or diverges. Let's take a look. Example 2. Let's go to example 2. Does this series diverge or converge? Now we are going to use integral test. So first step, let's set up our integral. Our integral, so it's going to be improper integral. So integral start from capital N. For our capital N here, this is 1. So it's from 1 to infinity. And then we'll change this into our function. So this is fn. Our function is just to change n into x squared plus 1 dx. Okay, so this is our improper integral. I know you learned this in Calc 2, but it's maybe a long time ago. Now let's have a little review. What is improper integral? How to calculate improper integral? Improper integral, we set integral into t, and then we make t goes to infinity. Oh, you can say 1 to b goes to infinity. Doesn't matter too much. And then here we have the same thing, function dx. And now we evaluate this integral. And then at the end, we find the limit. The integral of 1 over x squared plus 1, actually this is arc tangent x from 1 to t. Okay. If you forgot the formula, you can take a look at calculus 2. Please review those. And now let's evaluate this definite integral. It's going to be arc tangent t minus arc tangent 1. Okay. Arc tangent 1 equals what? Arc tangent means it's the angle. For what angle? Tangent is 1, right? So that means tangent what is 1. Do you know what is tangent? Tangent what is 1? What angle? Tangent pi over 4 is 1. So actually arc tangent 1 is pi over 4. Right, so this is pi over 4. Now let's calculate the limit. T goes to infinity, arc tangent t minus, this is a constant, we can just take the constant out. And here this is like an arc tangent infinity, but we don't write down this way. We need to, let's evaluate what is arc tangent infinity. So that means tangent of what is infinity? If we take a look at the graph of tangent function, tangent function looks like this, right? Okay. And here should be negative pi over 2, and here is pi over 2. Is that correct? And tangent of what is infinity? So if we say here's infinity, tangent of what is infinity? It should be pi over 2. So tangent of pi over 2 goes to infinity, minus pi over 4. So the final answer should be pi over 4. And we know of pi over 4. In this case, our improper integral has a value, so we can say converges, right? This improper integral converges, so our series converges. So we can say our series converges. That is called the integral test. Just set up a improper integral and evaluate the improper integral and then solve it and find the limit. If the limit exists, converges, otherwise diverges. Now let's take a look at the exercise problem. The first one, n from 1 to infinity, 1 over n plus 4. The second one, (1 to infinity, 1 over x squared dx). Actually, in my example, I didn't say the function is positive, but it's better to say positive, continuous, and decreasing. Why is cannot increasing? Because if it's increasing, that means it's going to be unbounded. If it's unbounded, partial sum is going to be unbounded. So definitely it's going to be diverges, right? So that's why, okay? Positive, continuous, decreasing. Let's take a look at just 2 exercises problem, and you can try by yourself. I will give you the solution in a few minutes. For the first one, solution, we set our function 1 over x plus 4, and it's positive when x is greater than 1, right? Positive, continuous, and decreasing. So we set up improper integral 1 to infinity 1 over x plus 4 dx, and we turn this into proper integral 1 to t 1 over x plus 4 dx, and then evaluate this integral, definite integral, t goes to infinity, and this integral, which is natural log x plus 4 and 1 to t, and plug in the bounds. So it becomes ln t plus 4 minus ln 1, and ln 1 equals 0. ln 1, 0, right? ln x, that's the graph. So this one equals limit of t goes to infinity, natural log t plus 4. And what's this limit? We have the natural log function graph. You can see here, when t goes to infinity, y goes to infinity, right? So this is infinity. In this case, our series n plus 4 diverges. Okay, that's the answer. Diverges. Second one, what is the function? The second one, let me take a look. Integral of 1 over x squared. Same thing, we set up our function. Continuous, decreasing, positive. Okay. And we set up the integral. Turn this into limit 1 to t 1 over x squared dx. And what is the integral? Negative 1 over x, right? 1 to t. And plug in the bound. I like to switch the bounds and cancel with the negative sign in front. So it's kind of like 1 over x and t to 1, something like that. It's easy to deal with the positive sign. And the limit t goes to infinity, 1 minus 1 over t. And the t goes to infinity, this term goes to 0, so final answer is 1. And in this case, we can see 1 over n squared dx, actually n from 1 to infinity, converges. Okay, this is how we use improper integral. Next example, we are going to show that P series converges or diverges for certain condition. So firstly, I'm going to give you the definition for P series. What's the P series look like? P series is given by this one, sigma 1 over n to the p, n from 1 to infinity. And if we write this out, it's like 1 over 1 to the p, 1 over 2 to the p, 1 over 3 to the p, something like that. So P series, you can see actually harmonic series is a special P series because this is for P equals 1, right? And 1 over n squared is a P series. 1 over n to the fifth is a P series. 1 over square root n, this is also P series because that means P is 1/2. and this means p is 5. Okay, that's they all called the p series. Now let's take a look. Example 4. Show that p series 1 over n to the p and from 1 to infinity converges if p greater than 1 and diverges if p less equal to 1. So this is another example of integral test. I'm going to show you how to tell converges diverges of p series by using integral test. Same thing, first step we set up our function x to the p, right? And then we set up our improper integral. So n start from 1. Here our integral also start from 1. 1 over x to the p dx. Now solve this integral. T goes to infinity, 1 to t, 1 over x to the p dx. When we solve the integral, we usually like to simplify. Actually, we can use power rule here, but we have to change this into power function. So we change this into x to the negative p power, right? Simplify. So t goes to infinity, 1 to t, x to negative p dx. And do you still remember in Calc 2, the power function means integral of xn dx is x to the n plus 1 over n plus 1. That's the formula for the power rule, right? So here our integral becomes to x to the negative p plus 1. Here negative p plus 1 and x from 1 to t. And now because 1 minus p or negative p plus 1, this is a constant. There is no x. So I'm going to take this out of the limit to make the function easy. So I'm going to take this out. 1 over 1 minus p and then limit t goes to infinity. And now let's plug in the bounds, upper bound and lower bound. So t to the negative p plus 1 minus 1 to negative p plus 1. Actually 1 to any power is 1. Okay, let's rewrite. Minus p I'm going to write down this as this form. Okay. This equals 1. And we write this into denominator. Right. So now let's take a look. When p greater than 1, p minus 1 is greater than 0, right? Let's take a look at this value greater than 0. And the t goes to infinity. So we say when t goes to infinity and t to the p minus 1 also goes to infinity, because this is kind of some infinity to some positive power definitely goes to infinity. If it's negative power, it's in the denominator, but it's positive power in the numerator, so it goes to infinity, and whole thing 1 over t to the p minus 1 goes to 0. So in this case, our integral goes to or equals to 1 over negative 1 over 1 minus p, so which is 1 over p minus 1. That's our integral. That is when p greater than 1. Second case, when p less than 1. Okay, less than 1. When this is our integral. When p less than 1, so this is a positive. Right? P smaller than 1, this is positive. So sum infinity to positive power. So this term goes to infinity. So this goes to infinity. In this case, diverges. And the last case converges. Actually, there's a number. And number 3, when p equals 1, that is harmonic. And we already proved this in our example 1, so we can say this diverges. So for the p series, when p is less equal to 1, diverges. P greater than 1, converges. Let's remember this conclusion. Okay. For example, right now, if we have something like this, converge, because p greater than 1. This diverge. This diverge. I can give you some more example. Square, converge. So in the future, we can just tell converges or diverges by looking at the p, right? You can remember this. So if I give you something like this, we know this is 1 over n to the 1/2. Also diverges because p less than 1. So we can stop here. In this section, we totally did those things. I can give you a summary. The first, we introduce the harmonic series and we say diverges. And then improper integral, this and our series Fn, just An, they have the same converges, diverges, okay, have same. This is called integral test. And we did several examples. And the last thing, p series. When p greater than 1, less equal to 1. Greater than 1, converges and diverges. Okay, 3 things. We can stop here.